All right. So this is the January 2024 paper 2 physics. Right. So let's get into this paper. Question 1 reads as follows. Figure 1 shows a copper rod moving through a uniform constant magnetic field. This symbol here, the circle with the dots in the middle, represents the magnetic field coming out of the page. This is very important, right? The magnetic field is coming out of the page towards you, basically. So each end of the rod is connected to leads that are connected or leads that are connected to an ammeter, right? And that is used to measure current, as we know, right? Which measures the electric current. Now the rod is only allowed to move in a horizontal direction. Horizontal would mean, yeah, like this, right? Right side, left side. Left to right, right to left. While in the magnetic field. So figure 1, a copper rod moving through a uniform magnetic field. They say draw an arrow on the rod to indicate the direction of the induced current when the rod moves to the left. So the rod is moving to the left, right? Allowed movement of the rod here. But our movement would be to the left. So you can use Fleming's right-hand rule in this case, right? So Fleming's right-hand rule is used for induced current or generator, right? With the thumb finger would be the motion. In this case, it's to the left. So this is the motion. I don't know if I could draw this properly, right? But let's see. This is at a 90-degree angle there, right? And this is the other finger, right? And the rest just screw up, right? That looks kind of weird, but anyway, that is Fleming's right-hand rule. So this will be the current, right? More specifically, the induced current. So I'm gonna put induced current. This would be the magnetic field, and well, obviously that's the motion, but our motion is to the left. Our magnetic field is coming out of the paper, and well, the induced current is what we're trying to find. So we apply that rule here. So what we would do, the motion would be to the left. So your thumb finger should be pointing to the left. Now the magnetic field is coming towards you. So this let's call it. I think your first finger would be pointing towards you, and obviously I think your middle finger will be pointing upward, right, indicating the induced current, which will simply be something like it should give you something like this, right? That is the movement of the current there. When that's right over this, break it a little better, right? That is the induced current going upward there, right? This, yes. You just need one arrow, right? You don't need two arrows. So I'll leave that one there, right? So that's the induced current, and I say name the rule used to determine the direction of the induced current. So I just said it. It could be Fleming's right hand rule, right? This is to determine this is used for induced current, right? Simple. Also, our next, the Fleming's right hand rule, where the curl of your fingers will be the magnetic field. If you put it like that, the curl of your fingers will be pointing towards you, and your thumb will be pointing upward, indicating the current as well, right? But we can stick with this right hand rule here, right? So that was it. There are 2 marks. Part B now. Part B reads as follows. So an experiment was performed to determine how the strength of a magnetic field affects the value of induced current. Readings on of the speed of movement of the rod, which is U, and the current, induced current that is I, were obtained and recorded in the table below. Right? So speed of movement is meters per second, induced current in ampere, induced EMF, electromotive force, which is volts. Given that the rod has a resistance of 25 ohms, so that is resistance, that is R is equal to 25, my bad, um, 25 ohms, right? Use Ohm's law to complete table 1 by calculating the induced EMF. So if you did not know Ohm's law, you would not have been able to fill out this table here, this column here. So Ohm's law, right? Ohm's law is basically V is equal to IR. We have I values, which is the induced current values, and we have a fixed value for R, which is 25, right? So we just substitute that here. I will just do a sample calculation here. So sample calculation, right? Using the first row. So we just concern about the current value. So V is equal to I, which is 0.0045, not so, yeah, multiply by the resistance, which is 25, right? So V would therefore be equal to 0.113, right? Right. So what we gonna do here, we gonna write it in like that because this is to 3 decimal places. So all our values in this column here has to be to the same amount of decimal places. So you put 0.113. You work out the other values same way, like this here, this here. When you work it out, you're going to get 0.538. Right? Put my point there. Right. The other one will be 0.75. Now, if you would leave it at 0.75, that would not be, correct, the correct way of putting it. You would put your 0 here because you want to write it to 3 decimal places, right? 3 significant figures, right? So yeah, that's basically how to fill out the table, and that was an easy 5 marks. But you only have 3 values here, right? But they give you 5 marks for that. Obviously, they will give you a mark for stating Ohm's law and for doing your substitution, and then for having the correct values here, right? So they say using results from table 1 to plot a graph of induced EMF volts against speed of movement on the grid provided in figure 2, page 7, draw the line of best fit through the points, right? Right, so how I did this question is, well, I already plot the graph here because plotting this graph would have been a bit tedious to do and take up a lot of time when I'm trying to condense everything and make it simple, right? So let's see. So looking at my table here, I don't know to get the scale on thing as well. Looking at the table, we have induced voltage. Our largest value was 0.95, right? So after the erase this here, right? Our largest value was for this is our y axis. Our largest value is 0.95 minus our smallest value is 0.113. Right? That will therefore be equal to 0.95 minus 0.113, 0.837. How many blocks we have on our y-axis? This is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 24. But I could try to, fit it within 20 blocks. It just have to occupy more than half the y-axis, basically, divided by 24. So one block could be 0.03, but that's a kind of weird number, and it kind of hard. It will be kind of hard for me to read what is one small square. So I multiply that by 2. I get 0.06. Now I can't let every 2 centimeters be 0.05 because then I wouldn't enough. So what I could do, I could pick the next easiest number to read, which is 0.1. So every 2 centimeters, like here, I put 0.1. And this is easy to read because every small square will be 0.1 divided by 10, which is 0.01, which is easy to read. And look, it was enough. So I had 1, 2, 3, 4 squares remaining going up. So that's an easy way to figure out the scale as well for your y-axis in this case, right? Now the x-axis, you could do the same thing. 0.038 minus 0.0045. You divide that by you have 1, 2, 3, 4, 5, 6, 7, 8. 8 by 2, 16. You could let basically, let's see. Oh, it was speed movement, right? So 0.7. Oh well, yeah, 0.7. 0.7 minus 0.1, you get zero point 0.6. But I have a lot of big squares on my x-axis, so I can just let every 2 centimeters be 0.1, and that will be enough. Yeah. So that was just getting the scale. What you will get marks for is, first thing is labeling your axis with the unit. Induced current with the unit, induced EMF. I mean induced EMF, my bad. Induced EMF unit V, right? Symbol V. Speed of movement, U meters per second. You get marks for labeling your unit. As you may know, when you was doing labs and stuff like that in school, what you just get marks for ORR, for plotting the graph, right? You just get marks for, if your startboard axis at 0, 0, you have to put the 0, 0 here, like how I did it over there. X starts at 0, Y starts at 0. You just get marks for your scale, right? You will get marks for your best fit. Notice something. This line is, you could say best fit, right? The straight line passed through the points. It didn't pass through all the data points, but it passed through the points evenly, which means that the spaces the points are above the line would be equal to the sum of the spaces the points are below the line, right? So it kind of passed through only it passed through the points evenly, right? It didn't need to like literally pass through the data points, but the points just kind of scattered a little bit, so it went in between it, in other words, evenly. Right? So you get marks for that. You get marks for correctly plotting your points. So this one is 0.1, 0.11, I believe. Let's see. 113. But I plotted kind of, well, you don't have it to 3 decimal places. You just have it. You could get it to 2 decimal places here. Next one is 0.2, 0.275, 0.26765, like that. Right? So I know all these points are correct, right? So you get marks for your points as well, right? So very important to know what you're getting marks for when you're plotting your graph, right? You could always use as a guide to know how yours would come out or how yours did come out, um, to check your answer, in other words. So they say use your graph to determine the gradient G. Now if you scroll back up, did they say anything about the gradient? No, they didn't say anything about the gradient yet. So you're supposed to know that gradient capital G would be equal to y2 minus y1 all over x2 minus x1. So you get a mark for just stating that formula there. Right? Very important. And now, since my points did not was not on my straight line, I have to read off some points now. So I mean, this one went through the origin 0, 0, so I could use that. So x is 0 and y is 0. Whenever you're stating that point, you always put your x first and then you put your y value. And the other point that I could use is, well, I read off a whole new point here. I get 0.64 and 0.85. Right? That is the point over here. Right? We come in and look, I put my 90-degree angle. This is what it does look for as well. The triangle must be bigger. It cannot be small. It needs to occupy at least half of the graph as well. The triangle. Right? And you just read the value going across like here. So, right? 0.85. 0.64, comma 0.85. Right? And obviously you put your x value first, then you put your y value, close your bracket. So you have to label them x1, y1, x2, y2. The first point I will label that as x1 and y1. The next point I will label that as x2, y2. Then what I will do here is substitute it into the gradient formula. So I just put in mark G because G represents the gradient, as what they had said here. So y2, which will be the 0.85 minus the y1, which would have been 0, divided by x2, which is the 0.64, minus the x1, which would have been 0. So G, which is your gradient, will now be, when you work out this, you should get something around 1.33. Right? But this is not your final answer yet. You need to put in something. You need to put in your units for your gradient. Right? So if we know that G is equal to change in y all over the change in x, but what we had on our y-axis, we had volts, V. This is the unit, right? What we had on our x-axis, meters per second. That's the unit. We just plug in the units. So our final unit for the gradient will be volts per meter second. When you bring the per second on top, it will just be second. So volts per meter second. And that is your answer there. So what you will get marks for is stating your gradient, reading off your 2 points, substituting your final answer with the units. Right? Those are like things you would get marks for. Right? So yeah, substitution. Right? Let's see. So they say the gradient G is related to the length of the rod L by this equation. Right? So in case you can see this properly, G is equal to 4.3 times L. They say calculate the length of the rod L using the answer obtained in B3. So we had found, right? We had found G to be equal to 1.33, right? I believe the unit was VSM to the minus 1, right? We want to solve for L, right? Let's say calculate the value of L. So you just make L the subject of the formula. If you know G is equal to 4.3 L, this is the same thing as 4.3 L is equal to G. Now you have 4.3 in front of L, but you just want L on the left hand side. So you can divide both sides by 4.3, right? The number in front of L, that will cancel off. So what you will end up with is L is equal to G all over 4.3. Or if you have 4.3, L is equal to G, Your carry across is 4.3 to the right hand side, you're going to need to divide. Because this is 4.3 times L, so when they carry it across, you got to do the opposite of multiply, which is to divide. And therefore, you'll get L is equal to G all over 4.3. Now, the reason why I did it both ways is because a lot of students still get problems making subject of the formula, right? Which should not be the case, but yeah. So L is equal to G, which is the 1.33 divided by 4.3. So when you work out this, you should get, this is 3. You should get something around 0.31 meters, right? And this is for L. So I will just put it here. L is 0.31 meters. Now, this, we know length to be measured in terms of meters, right? However, if you had used the units they had given you here, you would have VSM to the minus 1. I don't know how you would have getting meters there, right? So in a case like this, I wouldn't have used the unit for the gradient when I did the substitution. I would have just put my final answer as 0.31 meters. Or I would have put two answers on. I put L is 0.31 VSM to the minus 1 as well. Because that is just using the units for the gradient. You would have gotten an answer with this unit. But based on what you know the unit of length to be is meters, this one here would have been correct, 0.31 meters. Right? So that one was a bit confusing. But yeah, once you understand the concept here, basic substitution, it should be fine. So part C, the experiment shows that increasing the speed of movement can increase the induced EMF. Right? Right, increasing U would increase V. Let me go back to the data here. We could clearly see that as U values increases, gets larger, coming down, coming down, V, the values gets larger as well, right? So it increases, coming down, increases, coming down. Same for here, it increases, coming down, right? So hence we get the straight line graph and stuff like that over here, right? As induced EMF increases, speed increases, basically, right? So let's say I gave one other factor which would increase the induced EMF of the rod apart from speed. So I have a set of different answers here, right? But the size, right? The size of the force acting on the wire or the rod in this case will depend on the following, right? And I have a couple options here. The first one will be the current in the wire, right? So the current in the wire, or in this case, you'll put a rod, right? Now, the larger the current, the stronger the magnetic field around the wire, and the greater the interaction with the magnetic field from the permanent magnets, right? So you could say larger current, right? Larger current, the larger current, the greater, greater the magnetic field. The magnetic field around the rod, right? And the greater the interaction with the magnetic field from the permanent magnets, right? Okay. The second one I have would be the strength of the magnetic field. So the strength of the magnetic field, right? From the magnets, right? From the magnet, right? So a stronger field will produce a greater force. So a stronger field will produce a greater force. Very important to note. And this last one here, which is I believe to be the most important for this example that we did for this question, is the length of the rod. Of the rod. This is well more relatable to the question. Right? So the length of the rod perpendicular to the magnetic field. Right? Very important. This also affects the induced EMF. Right? So a longer rod will experience a higher EMF compared to a shorter one. Right? Very important to know. So a longer rod will experience a higher EMF compared to a shorter one, given the same velocity and magnetic field strength, right? Very important. Given the same velocity and magnetic field strength, you would expect this strength to happen here, right? I'll leave it as that for now because of the space and stuff like that. But yeah, this is just some options in which it just needed one, right? Let's say one factor, right? But I just give you three for future reference. That was basically question one for 25 marks, right? It was pretty simple and straightforward, right?